So, thanks to all the preparatory explanations from Matthias, I won't need to introduce the Jupyter notebook, and neither will need to clone the
just one thing. So you need to now, when you forked your repository, there were two notebooks in there, and Renato is now working on the second one. So you need to switch and open. There's in the upper left corner in Colab, there is file menu, and there you can open another notebook. You go to GitHub again, and then open the second one and run Renato's. Sorry.
Are we in the same page? Same thing you did before, but just now you have to put the address for the other notebook. And it's the beginning of the notebook is very similar. I have copied all the instructions that Matthias has put for all the forking stuff, but you have already done this, so you can skip these first cells because you have cloned the GitLab as well. So we will start from here in this cell. We will import the packages, and we will use some different packages in Python. And I also, okay, you have to trust. Okay. We will be using a package called Jensen that excels in building word models, document models, and a package called NetworkX for visualizing graphs. So I have already talked about NLP, and NLP in digital humanities is such a great help because we are, especially when we do corpus-based analysis, and Matthias was showing the power of named entity recognition in order to identify components of interest in texts. I will present you a slightly different kind of models. These are the word embedding models. These are ways to use neural networks to try to find words that are similar to other words, and we will do this in practice. Just to start with, I was telling some moments ago that we have, in order for the computer to understand text, we have to encode, and documents have to be represented in a mathematical way, vectors, in order to computers to be able to understand what is being manipulated. So what is the traditional way to represent word as vector? We have this technique called bag of words, and let's suppose we have 3 documents. I am feeling very happy today, I'm not well today, I wish to go to play. So these 3 documents have, they use a vocabulary, and the vocabulary that is used in these documents is this simple vocabulary: I am feeling very happy today, not well, wish could go to the play. So that the first phase when we are building document models, language models, is to establish what is our vocabulary. Once we have the vocabulary for our models, we can use attribution table, and we can assign. Okay, it is too short. We can use a table like this, where the columns are the words and the rows are the documents. So I can say the document 1 is made of 1, 1, 1, 1, 1, 0, 0, 0. Document 2 is also a collection of ones and zeros, and document 3. The problem is, for a language like English or German, we have thousands of words in the vocabulary. especially if we take things like different spellings and historical terms, we can have a huge vocabulary that is not easy to manipulate. So when we try to plot or to represent the words in a vectorial space, we would have here I can see a three-dimensional space, and each sentence would be represented by the sum of the vectors or the terms that compose this sentence. But if you imagine, it's hard for us to imagine spaces that are bigger than 3 dimensions. But can you imagine a space with 1,000 of dimensions? It would be hard to work with. And also, a space like this treats all the words as they were independent from themselves. And this is not the case. Words are very connected, and we can extract these connections based on the context where they occur. So if I have a huge vocabulary, I will have vectors that are mainly composed by zeros. And the word embeddings is one efficient way to try to capture this correlations among words. I can take 100,000 dimensional space, like a language like German, and try to shrink it into smaller components. Let's suppose we have this neural network here that uses an architecture. I'm not going too much into it. That established that every word would be represented by some weights in some dimensions. Let's suppose I have those animals. These animals are words, and I have these dimensions. To be an animal, to be domesticated, to be a pet, and to be fluffy. This neural network is able to extract these components from words and try to represent into smaller spaces. And so now each word would be a linear combination of let's say 200 or 300 categories or semantic units. And it was a serendipitous discovery that Nikolov, the Russian guy that made this in Google Lab, did. He found out that some nice properties can emerge of these spaces. We have some geometric properties that are captured from the language, from the model. So the same operation, let's say, multiply this vector by 2 or subtract this vector by this vector, can take words from man to woman, king to queen, or I can have flexions in verbs, or I can find capital and country, currencies and countries and things like that. These were discovered after the fact when they have applied these neural networks to create these models. And for historical periods, we can also, let's suppose we are training different corpus from different historical periods to our models. And we can see that some words are similar to other words in one epoch, but that can change over time. So I can even understand etymology and meaning transformations if I use different corpora to analyze words. But let's do it instead of talking. This first cell will download the German model. It will take a while, so please, could you run as soon as possible? As Matthias was showing, the German model trained on texts for for the name and the recognition. This model was trained in the German Wikipedia. So we have all the articles from the German Wikipedia. And of course, it's a biased model because the Wikipedia is a specific type of text with different constructions from historical texts and also from newspapers. So the model will bring the characteristics from the corpus it was originated from. Okay, you're maybe 27%. But the good thing about that is that you have the model in your notebooks. both the model that you have downloaded with Matthias and now this German model. And at the end of this session, we will create our own model based on the Ministerium corpus. Estimated time 2 minutes. Okay. So. Any doubt so far? You can follow this link, and it shows you the source of the model. It was trained in the German Wikipedia and German news articles in 2015. It takes a while because it's 700 megabytes big. And as Matthias was saying, that there is some evaluation source files. And what is the evaluation of a model? You take some domain questions that are made from the specialists, and we expect that the model can answer these questions accordingly. So we can evaluate the performance of a model based on a set of questions. So far, I am 79%, now it's going faster. So we are almost there. We are almost in our deadline for lunch, but I know you're not as hungry at that time. So. Okay, almost there. And after downloading the model, the next cell just checks if you have this model correctly downloaded. You have to see something more or less this size. Okay, so now we will use this model to, first we will load the model. We were downloading, now we are going to load the model. It won't take much. We will optimize the model, so just run this cell to remove the original vectors. And now we can check the words that are present in the model. So I put this word Frustu, and you can check. You can put any word you like, and the model will show. You can even put some part of a word. And the model and this function will show which words are currently in the model, and if they start with the subword that you have. We can check. This is out of curiosity, but you can check the vector representation of each word in the model. So I have here the word Wien, and Wien. By the way, is a combination of weights in 300 vectors. It has no meaning at all, but it's just to exemplify how these words is represented in this 300 dimension space. So far, nothing interesting, but now we are going to go to the nice part. We can use the model to check or to verify which words are similar to other words, and we can use some thresholds to determine if a word can be considered a synonym or related. So here I am comparing using two different metrics, the words Kopf, blah. You can change the models. So you have a live code here in front of you. You can simply substitute one word for other words, and you can check, of course, if the words are in the model. You can check how similar they are. And here we have .44, .55. They can be considered related, but not too much similar. Okay, so now it's time we can interactively use the model. Please change the words in the model, and we can see which words are similar to these words that you are changing. So I would expect you to change one of these words, and then we can run this cell. And for each word, we will have a column that will show us the most similar words to each word we have selected. So let's take blau as an example. We have hot, we have grün, gelb, orange, grau, blau. Hot is considered to be highly similar to blau. And Kopf, of course, we have here Kopf and Sperrangeweit often. I have no idea why these words are similar, but maybe you do. Gewerbe is similar to gastronomy in terms of the corpus. So the corpus gives us these measurements. We can also use this function to try to sort out which word does not pertain or does not belong to a set of words. So we have here blau, hot, feld, grün, and gelb. Of course, this is a very simple example, but you can, of course, change the words. You can uncomment this cell. You can make a comment in a cell and uncomment and even change the words, and we will have Frühstücken, Fenster, Abendessen, Mittagessen, and Soup. The word that does not belong is Fenster. Which other operations I can make? So let's go to the interesting part. Let's suppose we have two vectors, König and Frau, and we have a negative vector that is man. So in fact, I am summing up two vectors and I am subtracting one vector. And let's see what are the words that are most similar to this artificial vector that I have made. So I have some König, Frau, and I have subtracted man. And the word most similar to this operation is Prinzen, then Prinzessin, Königin, Prinz, and whatever. This is very powerful because we didn't know at the beginning what would be the result. So you can also change the words, try yourselves. You can make any kind of operation, summing vectors, subtracting vectors, and trying to grasp what would be the most similar, the result of these operations. Now we will use a mathematical operation. We call it principal component analysis. Because I say, we are using a 300-dimension space. We cannot visualize a 300-dimensional space. We live in a 3D world. We can only see 3D representations. But I can try to find out a projection of this space. What would be a projection? Let's suppose I'm looking to a 3D space by one side. I will project this space into a flat surface, and I will see the results. So now we can run this code and choose word pairs. Let's see what are the spatial relation between words. It's interesting because from Junge to man and Mädchen to Frau, I have similar operations. So I could easily find that the equivalent of Mädchen to this operation Junge and man would be Frau. I can do the same with man and Vater, Frau and mother. I can do the same with mother and Oma, Vater and Großvater. So there is an intrinsic homogeneity in the operations, in the linear operations I am performing in this vectorial space. Perhaps it's a bit abstract, but we are only interested in the results. I can use this set of words, the currencies and the countries, and I can see that there will be a similar graph out of it. Some things are different. Well, it's not exact, but I can see that I can go from. I can try to find if I know the operation I am performing. I can try to guess from my corpus what would be the currency for a country for which I don't know. And now it's time for you to build your own projection. So you will change the word as you like. I have put here Klein, Kleiner, Klein, Kleinste, Groß, Große, Groß, Großen, and I can see this projection. But I would invite you, I don't know if you have 10 to 15 minutes more time, I would invite you to change the cells and try to apply the same operations and see if the geometry would be more or less similar. And of course, you have to try to understand this projection as a 2D vision for a ND space. So if you change the way you rotate this space, you would have different projections. Okay, well, I guess you can do this in the break, in the lunch break. Another interesting thing I am going to do with you is to build a graph with similar words. Now I will use my model to take a seed word, and I can define the depth of my representation. I will take the word Österreich and build a graph like this. Change the side of the figure. You can change the word and try to apply some different graphs. Now I can explore the vicinity of the philosophers in a graph like this. And this graph is solely made from the similarities between the words. And now I have some exercises. I don't know if we will have time for this, but I would invite you to try to think about an experiment just using the code I have already provided to find any gender or racial or religious bias in the corpus, in Wikipedia. I would have to make operation like Catholic is to good as other religion is to. Let's suppose I would change. I cannot do this because I'm not a German speaker. But you could choose your analogies, changing this word. Two vectors, and let's suppose I am extracting. I would put here one religion, another religion, and one adjective, and I would try to find the equivalent adjective to this other religion. I can do this with gender, like instead of chronic, let's suppose I am, what is the word for engineer? I-N-G-N-I-E-R.
A U before the R.
Before the R.
Like in French.
Okay. So the equivalent for a woman would be electrotechnique. So there is a bias because an engineer is
that's again a male form, so electrotechnique would be again a male.
okay.
Tüftler also, electrical also, engineer is plural, engineers again. There are only male forms.
So that's good because apparently the Wikipedia is not biased, but it should have showed the equivalent word for woman. And you can play with this. You can explore this corpus and try to find what are the relations that it shows you. So this is one of the tasks I would propose, and the other, the last cells are small code to train a corpus out of your own text. So I'm using here this okay. Oh, that's because I haven't cloned the summer school. But you can run yourselves. You can create a corpus, create a model out of the NPR-T files. I have here a function that reads each file, cleans the HTML related, the XML tags and annotation, and you have only the remaining text. So you can train your model. You can train your model with a different set of parameters. Here I have the dimension. I am creating a 200 dimension space. I will use the window. The window is our parameter that says how many words in our window will be taken as related. So let's suppose I am sliding a window into a text, and this window is a moving window, and I'm always considering 10 words in this window. So if I decrease the window, the words that are considered in the same context will decrease. If I increase the window, the sliding window will be bigger, but maybe I can capture also spurious relations. So we can play with these parameters to build our own model. But if I build a model out of this corpus, I would have for the word minister. All these words are present in the corpus. And if I would try to find the similar words to ministerates, ministerium, ministerate protocol, I would find that these are the most similar words according to this technique. What that means? It means that for these words that I'm trying to analyze, these 10 words would be appearing in similar contexts. So I could use this model to try, for example, to find which are the adjectives that are related to one name, because these adjectives would appear in similar contexts. I could choose some named entities. I could use the named entity techniques that Matthias was showing to try to choose the entities I want, and I could try to find entities that are not in my model, just applying this kind of word embeddings techniques. So these are most supplementary techniques that can be used along with each other, and there are more, but this is just an introduction. If someone is interested in these techniques, I would be glad to receive your messages. My mail is in the program. And